Welcome to the third video in Unit 3 on probability theory. This lecture is going to cover expectation, variance, and finally covariance as well. As always, this is presented by EduOnics. So we've talked about a few introductory principles to probability theory. We've covered probability distributions. Now it's time to move on to expectation values, variance, and then covariance for the purpose of the covariance matrix and correlation. Alright, so let's go ahead and dive right in and get started. So, to begin, the expectation of some function f of x with respect to some probability distribution is the mean value f takes on when x is drawn from p, and p here being the probability distribution. So the expectation value, it can also just be called the expectation or the expectation value, is essentially going to be the average of the random variable that we are talking about, in this case x, with respect to its probability distribution. So you can have different probability distributions are going to have different expectations for the same random variable. Different random variables using the same probability distribution are going to have different expectations as well. Just think of it as the mean or the average value. And it's found a couple of different ways depending on whether or not you are using discrete or continuous variables. For discrete variables, as always, it's found with the summation. And another notation to note here is the expectation is usually written as this capital P, or the capital E, excuse me. And the x tilde p is x with respect to the probability distribution p, and then in the brackets you'll have the function that's being applied. This can be a function, it can be a random variable. In this case, the function is the random variable. So the summation of p of x for all states x multiplied by the random variable. For continuous variables, so f of x here is continuous, our expectation of x with respect to the probability density function, lowercase p, is going to be the summation or the integral of p of x f of x dx. So some important takeaways from this slide: notation, capital E, you'll often see it written without the x tilde p, and even in some cases without the brackets in f of x. The expectation is going to be a summation of the probability distribution times the random variable for discrete variables, and it's going to be the integration with respect to the x, the random variable here, for continuous random variables. Okay, so that's the expectation, and really the expectation is so useful because in probability theory it can be used to find the variance, and consequently it can be used to find the standard deviation as well. So the variance here, sigma squared, formal definition would be the expectation of the squared deviation of a random variable from its mean. And that is a little dense, so informally measures how far random numbers drawn from a probability distribution p of x are spread out from their average value. And that average value here being the expectation value. So here's the formula for that. The variance of f of x is going to be the capital E expectation of brackets f of x minus the expectation of f of x squared. So this is the squared deviation of a random variable from its mean or from its expectation of f of x. So this formula is pretty easy to implement, whether you're using R, whether you're using Python, whatever programming language that you are using, you're going to be able to find the expectation easily, and we'll take a look at that ourselves. Expectation, we're not going to go into example problems in this lecture. We'll leave some of that for the programming exercises that will follow. So one good thing about the variance is that it's really easy to find the standard deviation from the variance, because the standard deviation is simply the square root of the variance. And so consequently you'll see the standard deviation written as sigma, the variance written as sigma squared, since the standard deviation is of course just the square root. And so the variance and the standard deviation are two measures of spread. You'll see them both reported oftentimes in papers describing machine learning or AI applications. The variance and standard deviation come up all the time because we want to know what kind of distributions our input variables have. So we'll find variances and standard deviations. We can do some normalization tactics if we know the standard deviation or variance, as well as generating different probability distributions. You're gonna, like, let's say you're adding Gaussian noise to an image to make a AI system generalize better to new images. Adding Gaussian noise is going to be drawn from a Gaussian distribution, which is simply a normal probability distribution with a mean of 0 and then a variance of some value. So the variance you're going to define is going to determine how wide or how far spread out from the average value 0 values are going to be. So variance and standard deviation, very useful in practice and essential to understand moving forward. From the variance, we can find the covariance, and the covariance is going to be a measure of how much two variables are linearly related to each other. So the covariance of f of x and g of x, these two variables, are going to be found using the following formula. And again, the covariance relies heavily on expectation values. So some general principles about the covariance. High absolute values of the covariance are going to mean that the values change very much and are both far from their respective means at the same time. If the sign of the covariance is positive, then both variables tend to take on relatively high values simultaneously. In contrast, if the sign of the covariance happens to be negative, then one variable tends to take on a relatively high value at the same time that the other takes on a relatively low value, and vice versa. So other measures such as correlation normalize the contribution of each variable in order to measure only how much the variables are related. So rather than also being affected by the scale of the separate variables. So the covariance here, it is important to note that it is affected by scale. So the larger your variables are, the larger your covariance is going to be. Also, it's important to note that the notions of covariance and dependence, if we talk about dependent variables, x is dependent on y or x is independent of y, the notions of covariance and dependence are related but distinct concepts. They are related because two variables that are independent have a zero covariance, and two variables that have a non-zero covariance are dependent. Independence, however, is a distinct property from covariance. For two variables that have zero covariance, there must be no linear dependence between them. Independence is a stronger requirement than zero covariance because independence also excludes nonlinear relationships, and that is the key. It is possible for two variables to be dependent but have zero covariance, since covariance only measures linear dependence. So the covariance, oftentimes you'll use it when you're moving on to correlation, and we'll talk about correlation a little bit in our programming project. But the covariance is often used to find dependency, or at least linear dependency, between variables. If you had dependency between input, for example, into your, or different variables as inputs into your AI system, you'd want to note that because you can exploit that linear dependence to either compress your input data or produce better output results. So moving on from the covariance, we also have the covariance matrix, and this is what you're going to see most often. So the covariance matrix of a random vector x, and notice the x is bold to denote that it's a vector, is an n by n matrix such that the covariance of the vector is going to be the covariance of the individual components, x of I and x of j. Furthermore, the diagonal elements of the covariance matrix given the variance is going to simply be the variance. The diagonal elements of the covariance matrix give the variance. So we can find the covariance matrix, and then we can extract the diagonal, and the diagonal is going to give us the variance of x of I for the n by n matrix, or the random vector x. So the covariance matrix is essentially the the covariance applied in matrix form. And thinking back to our unit on linear algebra, almost all of our inputs, weights, activations, outputs, those type of things are going to be vectors and matrices. And so oftentimes when we're applying covariance, you're just going to go straight to the covariance matrix so that it can be applied in matrix form, since we're almost working exclusively in matrix form and matrix notation throughout machine learning. So this is the overlap of probability theory and linear algebra. It all comes full circle, the covariance matrix, and once again, we'll take a look at this in a quick R programming example, and so stay tuned for that. All right, so this brings us to the end of expectation, variance, and covariance. Again, just a brief introduction, talking about some of the concepts and the theories. We'll practice these concepts a little bit more in the programming project. In the next video, we're going to be talking about special random variables. We mentioned a Gaussian distribution in this lecture. A Gaussian distribution is going to be one of those special random variables and probability distributions. Just some of the things that you're going to see come up more often than not in AI and machine learning. So stay tuned for that. Thank you very much for listening.